The first speaker in our last session today is Professor Pramod Viswanath, who is from the University of Illinois, Urbana, Champaign. He also was my advisor there. And this session title is Related Topics.
Which everybody knows that is the last day, last session called Related Topics means unrelated topics. So this was my title, and I thought that's really related. You know, Chinese restaurant process, big data, learning, a little too related, and I had to watch out for the organizers. They put me on the last session called Related Topics means unrelated. So really, I'll watch out for the organizers and say that we'll do something unrelated. It's on anonymous messaging, and so there are two parts, messaging and anonymous. And messaging is how the world works, and if you missed the boat, Facebook did, and it cost them $16 billion to buy WhatsApp. And everything works on messaging. And then there is Slack, which replaces Office email. I mean, that's also messaging. And each one of these is, I think even the bottom one is definitely valued over $1 billion. And anyway, messaging is how people communicate. And there's not necessarily how. And that's the messaging part. And anonymity is something else, where some people want to say something, and it's pretty sensitive and important. People still want to say sensitive things, but maybe not quite as important. And so there are messaging apps you would imagine that cater to anonymous communication. So by anonymity, there are two kinds of anonymity. There is data anonymity and metadata anonymity. That means data as in what is the content? Is the content a secret or not? That's not what I'm talking about. I'm looking at metadata. That means, in particular, the source of who is talking. The content itself, we would like to make it as public as possible, but the source is what we want to hide. Okay. So there are messaging apps, and particular, if you have any middle school, college going kids, you have heard of YICAC. Definitely the phones have YICAC, and nothing else catches attention as banning an app in every high school, one block of every high school in the country. So that definitely catches people's attention. So there are these apps, and basically what they do is you can build, they're geography based, and you get messages from people in that geography. And you just don't know who it is from, it's anonymous. So secret is a slightly different, so somebody was trying to, this is messages at Illinois, so we get YICAC. So, all right. So secret is another messaging app primarily used in the Valley here. So people are chatting, but it's more socially filtered. So this YICAC was not really filtered. You get all kinds of messages. And secret is mostly socially filtered. So you get messages from your friends. You just don't know which one of your contacts. And all right. But the thing with all these messaging apps is that they're not really anonymous. There is a central authority that maintains everything, and you just have to ask them, and not even necessarily politely, and it's not anonymous. And so there is plenty of these kind of things, and they're even under federal wire type law, so they're actually stored. All the messages are stored, and they're not anonymous at all. And I want to think of anonymity at level of an adversarial scale, which is authoritarian. So strong adversaries, we should be able to handle them. And centralized networks are definitely not the way to think about them. So there are, anonymous communication itself has been around, and primitives exist. The onion router is a popular one, but they're primarily built for point-to-point. So you want to do from one place to another place, get to make an IP link and go through a bunch of routes, and the onion router is a pretty good one. We would like to do messaging. So that's really the point of this talk. And if you want to make it really unrelated, I could talk about the app we have. It's called Wildfire, and we could all download and play with it. But that may just, I'm happy to do that maybe offline. So, okay, so for this talk, we'll keep it more, so it has several interesting things. First of all, we'll be able to do, because it's a distributed setting, we can do lightweight crypto methods, and one can provide strong guarantees against authoritarian adversaries, and you can also play with messaging, and it's something that you can download on your phone and play. But just for this talk, we'll just do, it's an information theory session, so we'll do some likelihoods and probability of detection and some learning. Okay, so we'll skip this actual app. So the point is distributed messaging, and that's what I want to do. So in other words, I want to get away from centralized. There's no central server maintaining logs and tracks. Every one person would know who their friends are. Maybe they're in this context, I'm not so worried about the actual physical layer. So I'm maybe wired, wireless. I'm thinking it's an internet, so friends are just IP addresses. And I have a list of them, and I would like to communicate with them, and I have a message, I send it, and they like it, they hit the like button, it goes to their friends, and so forth. So what can an adversary do? First an adversary can maybe learn who got the message, who has the rumor. This is not very coarse-grained, maybe it has some side information on figuring out who got it when. The other one is they could also potentially, some of the users themselves could be spies, so they can collude. And when the users themselves are spies, they are privy to more information than just who got the message. They'll not only they know they got it, they also know metadata like exactly when they got it. And if that message came with some headers, control information, they know that too. And so spies come with these things, and really you have timing. Some nodes are colluding, and maybe you know who has what, so that's a little bit less coarse, not as detailed timing, but maybe you can get side information that way. And all about distributed network forensics is to figure out the author. So there's a long list of work in this area. Recent, I mean, this is a fast-moving space. Messaging apps didn't even really exist a few years ago, and this is very fast. And the corresponding network forensics are also new in distributed settings. And the traditional method is this thing called, so first you want to think of a social network as a graph. And throughout this talk, I'll think that the adversary knows the graph. Okay, so it's not, I mean, I want to give the adversary as many privileges as possible. So I want to work with authoritarian adversaries. So you want to think of how does information flow. Typically, you send it, an author sends it to one of his friends, and depending on when they watch it, they may hit like, and then it gets to send their friends, and so forth. This is usually how social networks work. Twitter works this way. One standard model is this thing called the diffusion model. It's been around. It's how messages spread on graphs and gossip algorithms. So this has been known, at least this community, we know how messages go on graph, at least with this random spreading model. And what do you do with this? Let's say we look at this adversary, which is sort of coarse. It knows exactly who got the message, but doesn't quite nail down, it's not any one of these nodes, so it doesn't have this timing information. What can it do? Well, how does it find the message source? The point is it just tries to put a ball and try to find the center of this graph. Can eyeball things and say, that's the center, and that's probably the source. Then we have to define what center means, and there are different variants, and there's this thing called the Jordan center, which just looks at the longest distance from one node. You pick a node, and the Jordan centrality or the eccentricity of that node is how far each node is, and take the largest one. You can look at distance centrality, which sums up the distances, and rumor centrality is a little bit different in the sense that it weights differently for degrees. So degrees may be not homogeneous. In any case, the point is, if you just have diffusion, one of these centralities really works. It's an inference problem. You can do the maximum likelihood. You can try to do the likelihoods of each source being the author given this particular realization of the graph. And here I'm plotting the likelihood in a color-coded way. Dark colors means high likelihood, light means low likelihood, and you'll see that the central nodes are the ones that are more likely. And so basically random spreading, just you can de-anonymize, even though it's distributed. The fact is the likelihoods concentrate and around the source. You can catch them. And this is not our result. This was popularized by Devrat Shah and Tawhid Zaman in a 2011 paper, and there are several works following up on this. Theorems are not as many to come with, but practical experiments are quite conclusive. Even if you don't find exactly the source, within one hop you'll find it, something like this. So diffusion is not enough. You can just distribute it is not enough, in other words. That's what I want to say.
What is this information that the adversary has here?
Oh, this one is this adversary here. The adversary just knows the underlying graph throughout, and here it knows which of the nodes got infected. Sometimes the adversary may also know which nodes got infected. Well, if the adversary knows everything, that means it knows all the nodes that got infected and has timing information on all of them, then it can just sort. And in some sense, that's a success, because if you can get an authoritarian adversary like NSA to snoop on everybody's phone, then you've won the game. It's to the extent that you lost it, you've won it. No, that's the point. I mean, you don't want to make it hard for them to snoop, put enough barriers. So in this one, there is no timing, and they can do it. So how do you do with timing? Let's say you may not know all the nodes. So you now know some of the nodes. And again, I'm using the color here. Dark colors means, let's say the message was earlier. Light colors means it got later. And now you don't really want to do the center, because somehow the darker colors are near the darker colors are where the source probably originally started. And so you want to somehow weight the distance information, the distance and centrality notions by timing. And again, there is a long line of work where, I mean, in practice, 5-10% of nodes, you don't need to know all of them. 5-10% with timing helps you de-anonymize. There's an early work of Pinto, Patrick Thinan, and Martin Witterly in the physics review letters, and several works later. I'm just referring to the early work in this area. Point again is that if you follow diffusion model with timing, without timing, you really get to de-anonymize. The catch is, our goal is really the opposite. I don't want to actually find. In fact, I want to make this job hard. And I'm fine, actually. I take both sides. That's why it's a spy versus spy, which is, for a given model, we'll try to find the best possible adversarial attack, and vice versa. I mean, we'll try to do the best on both sides. And without timing or with timing. Yes, David?
Pramod, I don't quite understand this timing information, because if you have timing information for every node, then you know the first guy must be the rumor.
That's right. And that's a win, actually, because that means the adversary put in so much effort to learn everybody's timing. In some sense, it's a win. That's really the final goal of this project, is that you put so much burden on the authoritarian adversary, that they really have to subpoena every single person. At that level, you really are out of luck. And it's a win, actually, I think, if you get to that stage. So we want to put enough burden that, adversaries are authoritarian, but not that authoritarian yet, luckily. They can sniff links and, not getting to everybody's phone yet. And if they do, then I agree, that's it, actually. There is nothing else one can do. In some sense, the goal is to get towards that, to make it hard enough. So I want to engineer the spread to hide authorship, to make it as hard as possible to find. And there are interesting problems on their own, without timing and with timing, and I think both are interesting, and turns out there's one solution for both. And that's what I'll talk about. And that's this. So point, I guess, is that if you do diffusion, it just doesn't work. So let's try with lines. This is the simplest kind of a graph. So the next 5-10 minutes, I'll just play. I only have 5 minutes. No?
No.
Okay, so 10 minutes, good. So I'll spend a few minutes just playing around with some simple graphs, so that way we get an idea of where we are coming and where it's going, and then I'll try to put together a system around it. So if you do a line, that's the simplest graph possible. The red one is a source node, and you start going on both sides independently. Then you try to find the author, you try to do the likelihoods. There's clear concentration around the center. I mean, it's not terribly concentrated in the sense that it's a line, so you still have some hiding, but you have this Gaussian type central limit theorem, and so the node in the middle is probably very likely, is the most likely one, and there's still some hiding, but the probability of detection is at least there's some hiding, so it's 1/√n. So on a line you get some, but I want to do better. I want to do 1/n. I want to hide everybody. So even an edge one could just as well have been likely as the other edge or the center. That's what I really want to do. And diffusion doesn't get there. Diffusion makes this concentration happen. And on trees, it's even worse. So we'll see that. So how do you do this? And that's sort of the first, that's how we started the slides with. It's a Chinese restaurant process with only 2 tables. And then I discovered it's also called the Polya's urn process, where there are only 2 balls in this urn, one red and one blue. And with probability half, you pull one ball out. So I'll describe how the sample path works, and let's say the red comes out, and now you put it back. So it's kind of the opposite of sampling without replacement. Here you sample with double replacement. You put 2 back. For every one get out, you put that back, and you put one new one of the same color. And now you realize that there are 2 red and 1 blue, and the red is more likely again, because now there's 2 out of 3, you get it out, and you put 1 again, and now it suddenly becomes 4 red and 1 blue. So you see where the pattern is. You started off equal, but very quickly you become unequal. The rich get richer and the poor gets poorer. And the versions of this, the Chinese restaurant process is used to model such sort of clustering effects. That's sort of the machine learning and area. But here, how does it work? Why did I describe this process? One thing that happens with this in the simple Poisson process is that let's say if I tell you there are 14 balls in this urn, I don't tell you the colors. Turns out all these events are equally likely, which way they are split. That's the first observation. And so the way I want to think of it is that I'm running two separate Polya urns on this line, and I have two urns. Let's say red means I actually spread, and blue means I stayed. I didn't spread in that direction, and the two urns are going separately. And the adversary here doesn't have timing. It just knows the total length of the spread. So that means I don't know the total number of red balls. And the finding the author is tantamount to being able to sort of separate the red balls back into urn 1 and urn 2. So knowing which ones came from which. And because of this uniform, all events being equally likely, one can calculate the probability, the likelihoods, and they're flat. As opposed to the diffusion process, which had this central limit of concentration. And the detection probability is approximately 1 over n. There are some constants involved too here. Okay, so that's how you do it. So we call this adaptive diffusion. I mean, just not a very innovative name here. And the idea is that now when you spread, you not only send the packet, but you also send this control message. The control message says how far away you are and from the original source, and also how much time it took to get there. The point is, there's like a velocity parameter if you wish. The faster I got the message from the source, the even faster I spread. If I got it slow for some reason, then I make it even slower. Just like the Poisson process where the rich get richer and the poor get poorer. And so this is the probability of spreading is directly proportional to, is actually equal to the half distance, I mean how far away you are from the source, normalized by how much time it took. This is a very simple discrete time model. Okay, so that's how you keep doing this. And so again, no timing here. So I just give you a length, and can you find it? And one can plot it, and then now you get this full hiding. This is a very simple graph, and it's just a line. And so you already see the first intuition. Yes?
But if you get to see one message, you know who's the author.
Yeah, perfectly. So that was my next slide. Thank you. That's precise. I mean, yeah, we think about that. Thank you. So if there is one spy somewhere, and they got one of the messages, now it also got this control information, the distance and the time. I mean, it just needed the distance. You didn't even need the time. That's it. You're out of luck right there. Totally. I mean, that's exactly was my next slide. And so we need to fix that. But you quickly realize that I don't need to actually pass these parameters of this process. I only need to actually give you a sample path, sample all the entire process ahead of time at the source, and only pass the sample path as along, and now you can hide your source. So that's a pretty simple idea. So this is very sensitive information. The source always gets located. That's precisely what the point was. And I mean, it's a system idea. This is a system issue, and there are system ways to solve it, which is that the source already gets the entire sample process, one sample path of this process, and then you just pass that process along. And so it tells each node how long it has to wait before it spreads. And each node can just chop off its part so that it doesn't not even need it to the other parts. All right, so the control data is independent of the message author, and the one sample path tells you really nothing about who the source is. Okay, so and you can plot, so this time it's not as easy. So there's one more thing though. If the spy nodes, not only so control message is not very useful, but spy nodes do know something more, which is that they know the times at which they got the message. So that's another thing. Though these are not global times, so the only thing, they don't know when the clock started, so it's relative. And one can calculate the likelihoods again. It's a little bit messy, so it's not as simple formula anymore. But there is a closed form expression. It's just not very nice, and you can definitely plot it though. And the point I want to say is that the detection probability is like 1 over n, as opposed to 1 over root n. Okay, so that's the story, and for just lines. I mean, that's about as simple a setting as you can get. Yeah.
So the spies didn't know where the message came from?
It does know that that it came from somewhere in the middle. So I put down 2 spies because it's a line. I mean, you can have more, but it's let's say it's in the center. I assume that the source is in the middle. So, I mean, it's somewhere in between the 2 spies. Let's say it could have been on the left and right, and you could have missed it, but I made it easy.
If you have 2 spies which have separation of k, then it will be 1 over k, the detection probability?
No, detection probability will be 1 over k, exactly. Okay. So it's the length of the spies. Spies are very close, and you know the source is middle, then yeah, that's exactly what it is. N was the distance between the spies. Okay. But there's timing, so it's a sample path dependent probability. I mean, there are certain times when you can really know it, but those times happen rarely. So it's okay, so you can try this on a tree, so maybe everything works out. Diffusion doesn't, because there is heavy concentration. I mean, that's in fact quite bad. With diffusion is particularly bad. You don't even have this 1 over root n hiding. In fact, with some positive probability, you get detected. So random spreading is just not a good idea. And turns out, so let's try this Polia's urn process, the Chinese restaurant process, the rich get richer business. I just try it. Turns out it's really bad too. And I just tried the Jordan Center. It's again there's concentration. So what's going on? It doesn't work at all, and that's kind of a bummer. The point, I guess, is that because in a tree there's exponentially many paths. On a line there are only 2 paths, and you could sort of completely control the process with 2. That's all that was happening. They're all equally likely. But on a graph, as you go along, there's exponentially many paths, and with high probability there will be like a few nodes which haven't weighted at all. They've really spread all the time, and those 3 nodes sort of is easy enough to sort of triangulate the center. Loosely, that's what's happening, and in practice, at least you can run some simple centrality algorithm, and the source gets detected. It's just not a good idea. The point, I guess, is that I don't want to let every path go along on an urn process. I want to somehow control the way in which things spread. So one can do that, and in the interest of time, I'll just say that there is a way to sort of, again, there's a system issue now. So I want to control the spread. I don't want to let everything be independent, every path be independent across the exponential paths. So I want to sort of have only linear in the time, as many paths going along, and I can control that. That's for a later talk. For a longer talk. Okay, so if you and the point, I guess, is that if you try to calculate the detection probability on a regular tree, it's quite nice. In fact, all nodes are equally likely except what is actually in the center. And so that's sort of our main result. I mean, in a talk like this, I mean, I've been watching this workshop in person today, but also in streaming, and there's always a theorem, and this is sort of our theorem. Yeah, so that's, yeah, I think every talk had a theorem, and I know this is related topics, but I should have one theorem. So one can do more general graphs. I mean, the whole point is that we have a messaging app, and we would like to work on it. I mean, the regular trees don't happen, and there are all kinds of real things. First of all, there are cycles. Degrees could be very different. Some people are, a lot of friends, and there are other people like me. And there are boundary effects. Some people just don't have any more. I mean, that's it. They just have one friend, and that's it. They don't have anyone else. And there's nothing else to spread. So there are all these boundary effects, and the algorithm sort of can get adapted around. We don't prove much about this. But I'll just say that the likelihoods can be approximated. They can't be found exactly for a given graph, but one can approximate it quite well numerically. So, and at least you know that the adversary can't do much, even if it did something like a maximum likelihood rule. So we're working on this. There are many interesting issues. I want to maybe not just hide the source. I want to also hide the relays. We are interested in, so this is like a dissent network. People are protesting, and there are authoritarian governments around, and yeah, and so these are, we want to think of these tools as basic primitives to work in a more protest setting. So systems are also interesting. I mean, I would like to really think of video sharing. Messaging is fine, but video sharing is, I mean, if you follow the trend, this is a very popular thing, live streaming of your life on messaging. I mean, this is the most popular app today. And in a distributed setting, there are issues like, if somebody went offline, how do you cache the message? So there are all these system issues. One thing that is, so this talk was really about anonymity, but one thing I don't want to be anonymous at all are the authors of this talk and this work. Yeah, that is, I want to publicize loud and clear. So this joint work with all these people I really enjoy. So let's start with the last. Sevung, he's having fun, and he's also a fun guy to work with. He's my colleague at Illinois. Peter Kerus is my graduate student who's been working on this project, and Julia Fanti is a student here, and she's here, and at Berkeley, and much of this work was done when she was visiting us last summer. And thanks to Kannan Ramchandran, with whom we've had several discussions on this topic.
Thank you. We can take a question while the next speaker can set up. Any questions?
I just want to say that there is a paper on archive, and that has some theorems, and yeah, Yihong.
What's the connection to the previous motivations about for example, if you are designing software, you can really control the user, the timing, right? You want to send a message.
What this, what this does is to put sort of an added delay on top of that. So people have some social filtering. You're right. Whenever they want to press like, they press the like. But on top of it, this will put a delay that's proportional to that.
So like add some noise to
You could say that exactly. I mean, the idea is to sort of kill the timing. The timing is usually a killer in these forensics, and we want to mess with the timing. Yes, Aaron.
To hit spies in the network, right? Do they follow this protocol?
Okay, good question. They could mess up, but then you could do nothing beyond. So all the way with the spice, we didn't really care about what happened after the spice. So in other words, they could mess up, and we don't know what happens afterwards. So we can, in some sense, we waited until all the spies got what they got, and then they could collude. You're right. I don't know what might happen afterwards.
So your effective N is basically based on...
Limited by the spy. So I had a cordon. I mean, I went fast, but you can put a cordon of spies, and there, like you could say, like a boundary, and you want to hide as well as possible within the cordon.
Thanks, Pramod.
I think your laptop is